Okay, so now we have the pleasure of having Jinzhao Wang, who will tell us about what exactly does Bekenstein bound.
You want to? Okay. Yeah. Okay. Thank you for having me here. Today I'm going to tell you something new about Bekenstein Bound. It's a work based on this archive submission with Patrick Hayden. So we're going to try to put an update by the end of this year, which may contain some new results. While information is physical, and I think Bekenstein Bound is a very nice illustration of this principle. So what Bekenstein found in the 80s is that so he conceived this thought experiment that and he concluded that the information that contained in any box of size R and which has energy E should not be too entropic, but otherwise you can dump into the black hole and violate the second law. He concluded that roughly speaking, the entropy should be less than up to some constant R times E. And interestingly, although the thought experiment involves gravity, in the end, there's no G Newton in this formula. So he conjectured that this is something that is universally true in relativistic quantum field theory. However, it remained unclear for a long time that how each term should be precisely defined in quantum field theory. It's a well-known story that Cassini in 2008 proposed a precise reformulation of the Bekenstein bound in terms of relative entropy. He observed the fact that if we just consider the relative entropy between any excited state of the vacuum over some region, say B, and then we can write it in terms of the difference between modular Hamiltonian and the entropy. And the positivity of this quantity of the left-hand side by definition is positive. So the bound sort of follows just from this fact. One caveat is that this formula isn't exactly correct in quantum field theory. So if we want to use it, we need to make sure that nothing blows up. And one way to do that is just to subtract by hand the vacuum contributions for the entropy and energy. And if you do that, really what is in consideration here is the vacuum subtracted entropy and being bounded by the modular energy that is set to 0 at vacuum. Okay, so this is what Cassini found. And a canonical example is that if we just consider this B to be a ring to the wedge, and then we see that this modular Hamiltonian admits this very nice local form that is manifestly of the form RE. In general, this is not the case for any regions or in any quantum field theory. Okay, so let's try to get a better feeling about why Bekenstein bound has something to do with the distinguishability measure. Okay, so let's consider the so-called species problem, and this is a procedure that we try to pile up entropy in Minkowski space just by simply increase the entropy without increasing energy by introducing more species. So the entropy grows simply because you do not know which particle species has been created. And naturally, if you consider the global state, the entropy of this mixture will grow like log D, with the number of species. Now the question is, what if we just put this presumably well-localized wave packet in a ring to the wedge? What about the entropy of this reduced state? Does it still grow like log D indefinitely or not? So it was a key observation by Maroff et al. A few years earlier than the Cassini's work. They show that, in fact, if you just compute precisely in quantum field theory this vacuum subtracted entropy, you'll see that it does not violate the Bekenstein bound. It will grow like log D until it hit the ceiling that is imposed by the Bekenstein bound, which is roughly, in this case, set by beta times omega. Now we can understand it in terms of relative entropy because we can check that when this thing is saturated, the relative entropy between the whatever state you consider against the vacuum is really becomes indistinguishable inside this region. So this means that the signals you would like to extract from the species become becomes messed up by the thermal fluctuations. And when D increases, the harder job to distinguish them against the background thermal noise. Okay, so that's why that's how we should think about Bekenstein Bound in terms of state distinguishability. Okay, so but a concern we could have is that this is essentially a reformulation of a bound. It's unclear what kind of information is being bounded here. So by which I mean that in quantum information, we like to think of the von Neumann entropy as the ultimate compression rate of the information source. But this operation meaning becomes somewhat obscure in this case after the vacuum subtraction. Because essentially, like, you can have a situation in particular that both sides of the Cassini bound can be negative. This will happen when you have some local, consider a region with a local negative energy density. And then in this case, yeah, it's clearly that it won't be a compression rate. So now, so this begs the question, could there be other versions of a bound that are just more operationally meaningful? So what do we want is something like this, where the left-hand side depends on a precise information processing task, and that characterizes the task. There will be some information measure that characterizes the performance of the task. And the right-hand side is just something that depends on the physical parameters that carries the information. Okay. So the setting we're going to consider this question is quantum communication. Why is that? So we would like to build upon the lessons we've learned from Cassini's result, that a good way to think about the Bekenstein bound is state distinguishability. So you can think of the task of quantum communication as basically a more elaborate version of this problem, where instead of just consider distinguishing a pair of state, now you want to distinguish a bunch of states that encodes your message. So this was previously considered by Bekenstein himself in the 80s in a somewhat heuristic way. And a couple of years earlier, there's this result by Raphael that he uses Cassini's result to show that to derive a bound on the so-called whole-level information, it's the information measure that is related to the classical capacity of a communication channel. So notice that so this quantity is defined for ensemble states, which you can think of the code words, and the probability is the probability of this of the message. And so this quantity is essentially a difference between entropies, right? So even though these code words are QFT states, which might be whose entropy might be UV divergent, but this difference will be finite. So this is the upshot of considering a quantity like this, is that this is by itself UV finite. You don't have to cancel the divergence by hand yourself. And also this quantity is operationally meaningful. So I guess these results motivate us to approach this problem a bit more using tools from quantum Shannon theory. And in the context of Shannon theory, the information measure is going to be given by the channel capacities. And of course, there are many channel capacities. The exact measure would have to depend on the communication task we have in mind. Okay, so the capacity is just a function of the channel, right? So if we want the Bekenstein bound to be relevant, we have to somehow constrain the channel either in spatial extent or in the energy budget. So there are just three natural ways to do that by either just constraining the encoding side of the channel or the decoding side of the channel, or maybe both sides of the channel. So I will not have time to explain this in detail, but it has been explained by Raphael in this paper, for example, that option one simply doesn't work. So if you just consider a communication scenario where the encoder is constrained, but the decoder can still see everything that happens in spacetime, then there will be no constraint on his ability to decode the state. There's an earlier formulation, this early attempt by Don Page on the Bekenstein bound problem, and he himself gave a counterexample to his formulation. And you can think of, if you look at why this proposal fails, you'll see that it's essentially because he just constrained the encoding. So option 1 doesn't work. And I will say that it's fair to say that the option 2, that is, you want to consider a Bekenstein bound that just pertains to the decoding, is the most natural one. And this is because in the usual way we think about Bekenstein bound, we just want a statement that holds for any state. Like we care about how much information we can read out from the state, no matter how the state is created for us in the first place. So implicitly, we do not care about the encoding part. In the usual way we think about the Bekenstein bound, we just care about how much information we can extract from it. So this is more in line with how we usually think about it. So we will primarily discuss option 2 and see if we need to also constrain the encoding later. Okay, so just to be concrete, we're going to consider a setup where we have the most control of, that is window space. So we're going to set up the problem by allowing Alice to be maybe a group of people that she really can control everything in the space. And what she want to do is to send a field theoretic signal to an accelerating Bob, who unfortunately only sees half of the space. And the question here is how much information can it communicate? So of course, there are many ways to do this encoding. So we're going to restrict to a situation we call the en route channel. So this channel enforces that Alice will encode her message as a single particle excitation in an en route mode of a distinct particle species. So this just means that for orthogonal logical states, she will encode them as distinguishable states of different species. And the noise comes from the fact that Bob does not see the left Windler wedge. So this will give rise to the en route radiation that will mess up Bob's ability to read out the message. Note that so this en route mode is really a global mode that's obtained by analytic extending the Windler mode. For technical reasons, we would like to make this choice. I will tell you why later. Here's the points that Alice needs really, we do not restrain Alice's ability in her encoding, or we do not even care about what resources needed to prepare such a complicated state. But the point is here, we just only want to focus on the constraint that pertains to the decoder Bob and see whether the Bekenstein bound would limit the communication between them. Okay, so the channel here is basically this isometric encoding, right? So that is described here, and followed by a partial trace over the left wedge. So this is the channel denoted by n, and it has 3 parameters. One is the input dimension, which is basically the species number that Alice can have access to. And second is the frequency of the mode, and also the temperature beta that also describes the mode. A sanity check that one can immediately do is that once we write down the channel, we can ask what's the entropy of the output for any input state. And let's check whether that is Bekenstein bounded. And indeed, we recover this result by Meroff et al. Right. So you can see that this is upper bounded by basically beta times omega, and this quantity is the same when you evaluate on any code word. Okay, but of course we do not just care about the entropy. We care about channel capacities, right? So what are they? We are interested in the ability of this channel to communicate classical message as well as a quantum message. So these are defined as optimal rates to transmit C bits, classical bits, and Q bits over IID, that means identical and independent uses of the channel. So the important point here is that really the exact capacity measure, denoted here as C and Q, depends on what kind of requirement you have for Alice and Bob. So let's look at the classical case here. So in the classical case, we demand that Alice and Bob will come up with their choice of encoder and decoder, such that after this process of communication, you want the code words to be distinguishable. That is, for any message of Alice X, Bob's decoding should be, the error rate should be very small. If you have this guarantee, if you can achieve this, you basically ask, okay, so how large you can make the size of X, which is denoted here by K. And of course, you measure in terms of bits, so you take the log, and of course, you use many times of channels, so you divide by n, and you want this to work. So you care about this asymptotic limit. And this will give you a function that only depends on the channel. Okay, so this is what we call the classical capacity. In the quantum case, everything is the same, except that we have a different requirement, right? So the rules here change a little bit. Now we can think of this input being also quantum, and being quantum means that it could be potentially correlated, entangled with a reference system, which we do not have control of. And by sending quantum message, we demand that we want to keep whatever entanglement this message might have between the environment, okay, or any reference, any purification. So mathematically, it's just given by this fact that the concatenation of these three channels should be close to identity in the relevant in the diamond norm, which is the distance measure for channels. And yeah, and the quantum capacity is basically the how large the value you can push the dimension of the input. Okay, so you can see that the key point here is that these two quantities are different, and they're different simply because we demand different things. Okay, the rules of the game here are slightly different. And the pioneers of quantum information, they already worked out for us the formulas, right? So here's the other definitions, and the formulas are given in terms of some entropic measures. For the classical capacity is given by the whole level information optimized in some way, and for the quantum capacity is given by the so-called coherent information that basically compares the output entropy versus the entropy of the environment. And again, the key point here is that the UV divergence was just cancelled because these quantities are just differences between entropies. Annoying thing is that in general, these things are not easy to evaluate because you have to take this limit, which makes these things very hard to evaluate or even just to upper bound it. Fortunately for the en-route channel that we sort of engineered, that this thing has additive capacities. So basically, that means that this capacity are just simply given by these quantities without taking this limit of many copies or many evaluations of n. So this makes it very simple to calculate. And what we want is to evaluate this and compare them to the Bekenstein bound. We find that basically now flash through the results. You can see that basically they obey the Bekenstein bound, just like how the vacuum subtracted entropy obey the bound. In the left here, I tune the temperature. On the right here, I fix the temperature by tuning the number of species, the input dimension, and you can see that nothing funny happens. Okay, so but that's a bit down. It's a bit down just to try to conform to the bound. What we really want to do is to try to challenge it, right? So it's more fun to challenge the bound. And how do we do that? Well, as I explained to you, the information sitting on the left-hand side of the bound really depends on the rules of the game. So here we're gonna, if we're gonna try to challenge it, we should think of a task that is less demanding. If we think of a task that is less demanding, then we have a chance to increase the left-hand side and then have a chance to violate the bound. So it turns out there is such a task that is less demanding, and yet is still a quantum communication task that Alice and Bob can play. So in this game, Alice just wants Bob to simulate any effect of binary measurement on her input state at Bob's output end. So what exactly do I mean? The game is that Alice will just pick any state in her hyperspace, and there's some referees is going to pick also some measurement, projective measurement on the state. But of course, Bob's task is to simulate the effect of this measurement on the output of the channel, right? Because Bob is not sitting with Alice, so all he can get is the output of the channel when Alice sends this state through, and Bob needs to come up with some measurement that as if it is as good as he measures directly the input state. So epsilon here is the quantifier for the quality. So in words, basically you want Bob to be able to ask, is the state phi or not phi, as if he is with Alice and measure her input state directly. Okay. So this is the task. And you can see that this is weaker than, say, classical communication. There you have to really ask to distinguish all the states. And here we just need Bob to ask these sort of binary questions. And we can sort of give this bits a name that is in the literature is called 0 bits. You might have heard of it in the context of black holes. But here it just means how large the k is for which you can play this game with a small error. And we let this maximum log k to be the number of 0 bits transmitted by the channel. So when we say the channel has the ability to transmit log k 0 bits, we really mean that they can play this game very well. So this maximum value is called the 0-bit capacity. Okay, so now we have changed the rules of the game to play this weaker version of communication, and this abstract resource transmitted is called 0-bit, and you should think of on the intuition level as a weak form of quantum information. It's useful in many other contexts as well. Okay, so now what about the number of 0 bits transmitted by channel? And we can see that indeed this will violate the Bekenstein bound. So in particular, if you look at the picture on the right here, where we fix the bound, but we return the input dimension, the number of species, this thing will grow like log d. Okay, so in essence, basically we have the species problem. And any bound, any physical bound you want to put here will be violated eventually. Okay, so this is the first punchline. There's no Bekenstein bound for 0 bits. Okay, so now is there anything we can do to make the situation a bit better, to maybe also bound the 0 bit? Now we can do that by considering also constrain the encoding. Right, on top of the constraint we already put on the decoding. So this is option 3 here. We want to constrain both. To make the argument, I'm going to use another bound of Cassini together with Blanco. Now I'm just going to review quickly what's there. This is another bound of them. So this bound just concerns, let's say, a slice, and A is a half space, and B is A is a half space on the left, and B is a half space on the right, and they overlap over this strip region with L. And if you consider this combinations of entropies, and these guys show that this is upper bounded by 2 pi times the length times the global energy of the state. So they figure this out by applying strong subjectivity twice over for the entropy of A and for the entropy of B with respect to moving from here to here. Okay, so you can sort of rewrite this left-hand side and package them into this more compact form. That is the difference between two mutual informations. And to do so, you need to introduce a purifier that purify the state row. And you can also see that this would make the bound, actually this bound is trivial for a pure state because the left-hand side will be 0 for pure state. You don't need the reference if the row is pure. But anyway, so this is what they proved. Okay, so why this is going to be useful? So because we're going to consider a situation that Bob is still sees just the right window wedge, but now Alice is also constrained, right? So she's no longer allowed to prepare like a global mode, like an Unruh mode, but she is only allowed to act on her left half space. But maybe she will act in the past, and this mode will only affect the future light cone here. And we want a situation such that at time to 0, there's this overlap region L. Okay, so let's consider any such channel that satisfies these geometric constraints. That is, Bob sees this wedge, and Alice only encodes in the left half space. And let this R be a reference that entangles with Alice's message, which we'll call A prime because A is occupied here. Okay, so now we can apply this bound to the state that is output by the channel. Okay, so it's easy to see that. So for this mutual information, which is basically the mutual information between this purely blue region and R, that this quantity should be 0, essentially because it follows by causality, right? So Alice is encoding, so R is only brought in by Alice's encoding, and there's no way that this should depend on R. Okay. So now you get a band that's only on one mutual information, and the state in consideration here is the output of the channel that only concerns Bob and the reference. And now this is good because we can just maximize over the input state, and this would be a formula that computes for us another capacity measure called entanglement-assisted classical capacity. This is a bit of a mouthful, but really it means is that it's the same measure for a classical capacity, but now Alice and Bob are given the additional power of shared bell pairs. So you should have in mind some extra systems where Alice and Bob shared unlimited number of bell pairs, which can be used to assist them in classical communication. Notice that this extra system is not accounted for by the Bekenstein bound, but nevertheless, their capacities are still limited by this bound. So the reason we want to bring this in is because it's not like we particularly care about this quantity, but it's the fact that this capacity bounds all the capacities we studied in the previous section. So all of the like the classical capacity, quantum capacity, and zero-bit capacity are all bounded by the entanglement-assisted capacity, which is bounded, which is Bekenstein bound. So now we can conclude that in this situation, so all the capacity we care about are bounded. And notice that this bound now pertains to both Alice and Bob, right? So this region is their overlap, and this energy is really the energy of the code words that Alice has to put into the state in her encoding procedure. Okay, so the second message is therefore, if we want to have all the capacity Bekenstein bounded, then it's necessary to restrain both the encoder and decoder. Okay, so I think that's actually all I have. So let me just conclude. So the first takeaway message is that there's generally no Bekenstein bound. There's no Bekenstein bound for 0 bits for general quantum channels that you can consider. In particular, we found a counterexample that for a case where we do not constrain the encoder. If you want to have the 0-bit capacity also bounded, then it's necessary to constrain both the encoding and decoding. And we show that this indeed holds for any channel satisfy a appropriate set of geometric constraints. Yeah, okay, that's all I have. Thank you.
I didn't understand why your Bekenstein bound depends on beta, because beta depends on Bob's orbit, how far he is from the edge of the wedge. And no matter where he is, you can see the whole Rindler wedge.
Right. So so beta comes in the in the en route mode. So yeah, it's a bit of a reverse engineering because the en route mode is obtained from analytic continuing the Rindler mode, and in the definition of the Rindler mode, there's a beta, right? So there's a scale I bring in.
More physically, beta only enters because of where Bob's location.
Right.
Bob is able to see everything in the Rindler wedge.
That's right.
From his location.
That's right. So it's
Matter.
his location shouldn't matter. Beta.
See, what you call a mega depends on Bob's location also.
Yeah, that depends on Bob's location also. Yes. So yeah, the beta and omegas already enters in this choice of Alice want to encode in the en route mode. Right. Yeah, yes.
I'm confused why you say that you need to restrict the encoding to sort of rescue the Bekenstein bound, because in the examples that you gave where there is a seeming violation, you sort of deliberately didn't use the definitions that Cassini provided for proving the bound. And in particular, you're not including the entanglement resource that's used for communication using using 0 bits. In the budget, in the energy budget, in the team you knew, right? Those things are going to contribute. I think they're being treated like they're free resource that's sort of outside the space-time.
So you mean this violation?
Let's be concrete. Let's say you try to do a 0-bit quantum teleportation.
Okay. Yeah.
To get this answer, you have to exclude the stress tensor contributions from the entanglement resource in that protocol.
I don't have any entanglement resources used here.
Implement 0-bit quantum teleportation. You need to have Alice and Bob need to share some entanglement.
No, so I do not have in mind any. Yeah, so to implement this bunch of stuff, I do need them. But here my point is that they just want to play this game, and yeah.
If you ask about a simpler task, then.
Yeah, that's right. But I do agree that if you want to combine it with other resources, which you can think of with other resources like entanglement pairs, you sort of turn these 0 bits into qubits or classical bits, and then these guys are Bekenstein bounded because of the fact that. Okay. Yeah. Okay. Yeah. I think yeah, there's a lot of flexibility of what information measure we would like to care about, and we care about whether, in this case, whether the 0-bit information is Bekenstein bounded, and I think in this case, regardless of what you want to use the 0-bit for, we can just think of it in a situation without additional help from a bell pass. And then in this case, I think if you do not restrain the encoder, then this channel will give you a counterexample to the Bekenstein bound. So that's why I'm saying you need to bring this additional constraint on the encoding.
Bekenstein's bound. You first have to redefine what Bekenstein's bound means before I took on the example of Bekenstein bound. Because there is a statement that Cassini wrote down, which is completely well defined. And nowhere in the world where you're doing this communication task is that statement violated.
Yeah, I agree. It's compatible with that statement.
Say it means something else than what Cassini taught us it means.
New Bekenstein-like bounds that have more clear
but it's very
information.
misleading. It's very misleading to say that you can violate Bekenstein's bound, but it's not the same thing that somebody formulated and carefully thought about and proved.
He's not claiming
To disprove Cassini's bound. He's mainly to prove another bound that he has proposed.
Yeah. That maybe means more, that has a more clear information direction.
I think we couldn't come up with a new name for it first.
Bound is not really Bekenstein bound.
Bekenstein's bound was not well defined. The first formulation of it that meant anything was Cassini's version of it.
Well, that's an opinion. I don't know.
Yeah, I was attempting a different version of the bound, right?
Thanks for a nice talk. Intuition for why the unroot channel has additive capacity, and is that only true in like a no back reaction limit?
Yeah, so of course here I don't consider any gravity, and so there's no question of back reaction. The en-route channel here is additive. Okay, so we use this fact called degradability which is a sufficient criteria for this channel capacities to be additive, and it roughly says that if you think about the channel, the output to the primary output and versus the information that dumps into the environment. This degradability criteria simply means that there's no extra information in the environment that you don't already know in the primary output. And so this means that you can have a map that maps you from the output to the environment. And in this case, I think intuitively you should understand this to be true is because the en-route mode is analytically extended from the Windler mode. And therefore, it does not contain more information than what you already know. So this is why we want to pick the yeah.
Will you make this a very simple question? Could you say what the en-route mode is supposed to be? Is it a mode relative to translations or Windler time?
Oh, so it's you take the Windler mode. You take a Windler mode, and then you rewrite it in terms of t and x coordinates, and you analytically continue. Therefore, it's a mode that's very oscillatory at the horizon.
Cartesian coordinate time.
No, it's not a Minkowski mode. Yeah, that's right. So it's a bit of a ill-behaved mode from a.
Terminology.
Okay. Yeah.
For the calculation, it's important that you're doing free field theory. Is that right?
Yes.
Well, the Bekenstein bound should also apply to interacting.
Yes. Right. So therefore, yeah, we do not have a general proof of, say, whether the classical quantum capacities are bounded for any channel in any theory. But yeah, we just want to illustrate the fact that this weak notion of information 0 bits, in this case, already do not satisfied with that. Yeah.
Okay, there are no more questions. Let's time to change our